So what if I told you that trying to make an artificial intelligence read a basic table of contents is exactly what will cause a highly optimized modern GPU to just catastrophically
I
crash?
mean, it sounds completely counterintuitive, right?
Yeah,
But it happens all the time.
right. And today we are looking at a developer who realized that the smartest AI frameworks in the world are actually doing way too much under the hood. And by trying to be helpful, they are actively sabotaging the hardware they run on.
Yeah, it's a fascinating problem.
It really is.
Yeah.
So welcome to another deep dive. And just to set the stage, this is a direct continuation of the Agentic AI series on the YouTube channel, RRAD to Riches AI. Our specific focus today is titled LlamaIndex plus NetworkX, very long GraphRAG story with a happy ending.
And honestly, that title is a massive understatement when you look at the raw engineering involved here.
Mhm.
We're dissecting a project where this developer, Vitally, set out to build a fully local, completely private agentic AI assistant.
And crucially, entirely confined to a standard laptop.
Exactly, completely offline. His ultimate goal was integrating GraphRAG so this local model could seamlessly search, retrieve, and display uncorrupted data from his personal knowledge vault, which, by the way, is an export of over 3,000 Synology NoteStation markdown files.
Over 3,000 markdown files. That is a massive amount of personal data. And he is doing this on an AMD Ryzen AI 9 processor with 32 gigabytes of system RAM, which, sounds spacious until you look at the real bottleneck.
Oh, absolutely, the GPU.
Right, his GPU. He is running an NVIDIA RTX 4060 laptop GPU with a hard limit of just 8 gigabytes of VRAM. And it's capped at a 54-watt power draw.
Yeah, and for anyone who has ever tried to run local LLMs, 8 gigabytes of video RAM is a suffocatingly tight envelope.
It's like trying to parallel park a bus in an alleyway.
That's a great way to put it. I mean, if you aren't careful, a single context window expansion will out of memory your entire system. You are operating on the razor's edge of physical hardware limitations at that tier.
Because in the world of enterprise AI, if a developer hits a memory wall, what do? They just spin up another AWS instance.
Exactly. They just throw money at the problem.
Yeah.
But Vitally couldn't do that. He had to push his hardware right up to the exact threshold of a CUDA failure, observe the specific memory allocation that broke it, and then write highly customized Python architecture to bypass those physical limits.
Which is exactly why we are diving into this today. Whether you are an AI tinkerer trying to squeeze maximum performance out of a local rig, or, you're just fascinated by the architectural mechanisms of how a machine can become a personalized digital companion offline, this story gives you a literal masterclass in memory management.
And framework optimization, yeah.
So let's unpack the baseline hardware setup. Vitally is running Ollama natively, and he has selected the Llama 3.1 8B model.
Which is an ambitious choice. Using an 8 billion parameter model on an 8 gigabyte card is pushing it. In standard 16-bit floating point precision, or FP16, an 8 billion parameter model requires roughly 16 gigabytes of VRAM just to load the weights into memory.
Just for the brain itself.
Right, let alone the context window for actually processing text. So to make this work, Vitally uses a quantized model format. By utilizing a specific quantization matrix, likely something like Q4KM, which is a 4-bit block quantization, he is mathematically compressing the precision of the neural network's weights.
So basically, he is squishing the model's brain so it takes up less physical space on the silicon.
Exactly, at the cost of a tiny fraction of its theoretical reasoning accuracy. But that compression brings the baseline VRAM footprint of Llama 3.1 down to about 5.5 gigabytes.
Okay, 5.5.
But then he also loads a Hugging Face embedding model, specifically all Milla LM-L6v2, to handle the vector math. And that consumes roughly another 1.3 gigabytes of VRAM.
Okay, so if we do the math here, 5.5 for the LLM plus 1.3 for the embeddings, he is sitting at 6.8 gigabytes of VRAM utilized before he has even fed a single document into the system.
Right, out of 8.
So he has exactly 1.2 gigabytes of overhead left for his context window. That is his absolute ceiling. But he still needs to index 3,000 markdown files. Now, standard vector databases like ChromaDB, which he actually is using for general document storage, they operate by chopping files into chunks, right?
Yeah, they chop them up, run them through that embedding model, and store them as mathematical arrays. But standard retrieval augmented generation, or RAG, is inherently destructive to formatting.
How so? Like for a basic user, what gets destroyed?
Well, when you take a highly structured markdown file containing PHP code blocks, YAML headers, and intricate markdown tables, and you force it through a standard recursive character text splitter,
Yeah.
you are obliterating the syntactic structure.
Oh, because it just slices it based on character count.
Exactly. You might slice a table in half right down the middle of a row. When you query the AI later, it performs a cosine similarity search, finds the mathematical chunks that match your query, and attempts to resynthesize an answer.
Okay, let's unpack this for a second. A standard vector search is like putting a novel through a paper shredder and then asking the AI to tape together a summary of chapter 3 based on the shreds it thinks look similar.
That is a perfect analogy. You might get the general semantic meaning, but the exact syntax of your PHP script is mangled. You can't just copy-paste the code anymore.
Which defeats the purpose of a coding notebook.
Right, and Vitally realized this, which is why he turned to GraphRAG. He wanted the system to map the relationships between his notes, but more importantly, he wanted the AI to hand him the exact, unmodified markdown file when he asked for it, like walking up to a card catalog that hands you the intact book.
So to achieve that structural awareness, he uses LlamaIndex because it has native markdown parsing and property graph capabilities.
Yes, a property graph maps semantic relationships as distinct entities rather than just flat text chunks. It understands that a specific text block is structurally dependent on a specific header.
Right, it builds a map of nodes and edges.
Exactly. For example, it maps that the entity MariaDB has a dependent edge connecting it to the entity Linux.
Okay, but to store a property graph, you traditionally spin up a dedicated graph database, right? And the industry standard for that is Neo4j. But Vitally explicitly avoids Neo4j. Why go out of your way to avoid the industry standard in a local build?
Well, Neo4j is robust, but it requires running a Java virtual machine or deploying a Docker container. Even the Community Edition consumes a baseline of 1 to 2 gigabytes of system RAM just idling.
Wow, just sitting there doing nothing.
Yeah. And while Vitally has 32 gigabytes of system RAM, meaning he could theoretically afford it, he is ruthlessly optimizing for zero overhead. He wants the most lightweight, frictionless pipeline possible, so he selects NetworkX.
NetworkX, which is a pure Python library, right?
Exactly. It operates entirely in memory. There is no external server process, no Docker container, no JVM. It just loads the graph structure directly into the dictionary space during execution.
So it's lightning fast.
Very fast. And when the script finishes, it serializes the entire graph down to a single flat JSON file on the disk. It is the absolute lightest architectural choice for managing a small to medium knowledge graph. You eliminate the latency of querying a separate database server entirely.
Okay, so with the stack defined Ollama in the GPU, LlamaIndex for the graph mapping, and NetworkX for the zero overhead storage, Vitally writes his very first ingestion script. He names it graphindexer.py. He points the script at his massive vault of 3,000 notes, hits enter, and the system immediately suffers a catastrophic CUDA out-of-memory crash. The NVIDIA driver just terminates the process.
Yeah, we need to look at exactly what happened in the VRAM during that execution, because his static allocation was perfect. 6.8 gigabytes utilized, 1.2 gigabytes free. The crash was triggered by how LlamaIndex handles asynchronous task queuing.
Wait, if he only had 1.2 gigs of VRAM left for the context window, and LlamaIndex triggered parallel processing, it would try to duplicate the key value cache for every concurrent thread, wouldn't it?
You've hit the exact mechanism of the failure. LlamaIndex, by default, is engineered for enterprise environments where speed is prioritized over memory conservation.
Because they assume you have massive server farms.
Exactly. So when Vitaly's script passed a batch of document nodes to the framework, LlamaIndex utilized Python's Essentio to fire multiple parallel requests to Ollama to extract the graph relationship simultaneously.
Even though Vitally had previously configured his system environment with the variable Ollama in parallel equals 1 to force a single stream.
Right. That environment variable tells Ollama to only process one request at a time. But it doesn't stop LlamaIndex from throwing 10 requests at the server's API endpoint all at once.
Oh, I see.
Ollama receives this barrage of parallel requests, and its internal Ollama server attempts to queue them up by spinning up parallel context slots in the GPU's memory. Every single slot requires its own KV cache allocation.
Which multiplies the memory footprint geometrically.
Exactly. That geometric multiplication instantly blew past his 1.2 gigabyte margin, triggering the hard CUDA kill. The software abstraction basically tried to be too fast for the physical hardware.
So Vitally has to explicitly throttle the framework. He imports the Nest-Essentio library into his Python environment to allow nested event loops. But more importantly, he completely rewrites the document insertion logic to be aggressively synchronous.
Yeah, he strips out the batch processing entirely. He initializes an empty index container, Then he iterates through his documents using a standard blocking for loop, running index.insert on exactly one document chunk at a time.
So forcing it into a single file line.
Right. The loop physically cannot proceed to chunk 2 until chunk 1 has been fully processed, extracted, mapped, and returned by the LLM. He guarantees that Ollama is only ever maintaining a single KD cache sequence in the VRAM.
So the system is forced to be slow but stable. He saves the script, runs it again sequentially, and the system crashes a second time.
Which must have been incredibly frustrating.
I can't even imagine. It throws another CUDA out-of-memory error on the very first chunk of the very first file. But this wasn't a concurrency issue, right? What was occupying so much memory in a single sequential request?
The culprit in the second crash was the payload density of the framework's extraction tool. In his initial build, Vitaly utilized a LlamaIndex module called Dynamic LLMPathExtractor to identify the entities and relationships in his text.
I've seen frameworks use these dynamic extractors. What are they actually sending to the local model's API under the hood? It's not just the text of the markdown file, is it?
Far from it. When you invoke Dynamic LLMPathExtractor, the framework constructs an incredibly dense, highly complex JSON schema. Essentially builds a massive system prompt that includes your document text, wrapped in a rigid instruction manual defining exactly how the LLM must format its output.
So it's telling it what the keys are, the data types.
Exactly. It defines the keys, the expected value types, nested arrays, and enum constraints. And the LLM has to load all of that framework boilerplate into its context window before it even starts reading the actual document.
Wow. And Llama 3.18b is a highly capable model, but forcing it to hold a massive multi-kilobyte JSON schema constraint in its working memory just devours the KV cache.
It does. The structural instructions alone were large enough to push the memory footprint over that 8 GB threshold. So to fix this, Vitaly does something fascinating because of how simple it is. He abandons the dynamic LLMPathExtractor and swaps it for the SchemaLLMPathExtractor.
Wait, really? Why does just dropping the word dynamic suddenly save his entire VRAM allocation?
Because the SchemaLLMPathExtractor operates on a much leaner methodology. Instead of forcing the LLM to parse and adhere to a massive JSON structural payload, it relies on significantly shorter, string-based prompt templates.
Oh, so it just asks nicely in plain text?
Basically, yes. It asks the LLM for the relationships in a more natural, text-based format, and relies on simpler back-end validation to parse the output. You drastically reduce the token count of the system prompt, which proportionally shrinks the KV cache requirement in the VRAM.
And to absolutely guarantee the model doesn't over-allocate memory, Vitaly hardcodes a limit into Ollama's configuration within the script. He sets numptx to 4096.
Right. He is explicitly locking the context window to exactly 4096 tokens. The memory pool physically cannot expand beyond that size, and he also implements a critical parameter change for the extraction phase. He sets the LLM temperature to 0.0.
Okay, I always see developers arguing about temperature settings for coding or extraction tasks. What is physically happening in the neural network when you set the temperature to absolute 0?
Okay, so when a large language model generates the next token in a sequence, its final layer outputs a probability distribution called logits across its entire vocabulary. A temperature setting greater than 0 applies a smoothing function to those logits, which flattens the distribution and allows the model to randomly sample lower probability tokens.
Which creates that sense of creativity or variation in the output.
Exactly. But for data extraction, you don't want the model being creative with your database schema. Setting the temperature to 0.0 applies an argmax function to the logits. It fundamentally disables the random sampling module.
So it just picks the most likely word every time?
Yes. The model simply selects the mathematically highest value token every single time. It becomes completely deterministic. This prevents the LLM from hallucinating complex, verbose outputs that would waste tokens, violate the expected data structure, and potentially crash the ingestion loop.
So no parallel processing, a lightweight string-based extractor, a rigidly locked 4096 token context window, and absolute 0 temperature. He points this highly constrained script at a test batch of 20 files, and it works, right?
It does. It slowly sequentially processes every single one of them without a single hardware failure. He successfully generates his first in-memory NetworkX database and serializes it to graphstore.json. The hardware straitjacket has finally been beaten.
Which is a massive milestone for consumer hardware AI. But ingestion is only the first half of the pipeline. The true test of an architecture is retrieval.
Absolutely.
So Vitaly launches his custom runtime interface, which he calls vectorterminal.py. He queries the system, asking for his original note on configuring MariaDB. And instead of receiving a clean, formatted markdown file, his terminal window begins vomiting thousands upon thousands of characters of raw .back file logs onto the screen.
Just endlessly cascading.
Yeah, it just cascades endlessly. It looks like the system has fallen into a catastrophic infinite loop, spitting out garbage memory data.
And anyone who has spent time developing terminal interfaces knows the visceral panic of a cascading text dump. It visually mimics a fatal memory leak or a recursive loop failure.
But when you look at the logs in the source material, the code actually executed perfectly. There was no infinite loop at all.
No, the reality of what happened is much more interesting than a simple bug. The graph engine hit a very specific natively handled Python exception. It threw the error. Entity node object has no attribute getContent.
Wait, how does a framework built entirely around processing text nodes suddenly encounter a node that doesn't possess a getContent attribute? How does Python perceive these nodes in the memory dictionary?
This requires understanding the internal node anatomy of the LlamaIndex property graph abstraction. When LlamaIndex ingests a document, it doesn't just create a single monolithic object in memory. It splits the data representation into a dual-layer architecture consisting of chunk nodes and entity nodes.
Okay, a chunk node sounds pretty literal. It holds the actual data, right?
Right. A chunk node is the literal data container. It holds the raw string content of a paragraph, a code block, or a markdown table. Within the Python object, it possesses a .text property and a callable .getContent method.
So when you ask the terminal to retrieve your original node, the chunk node is the only object you actually care about reading.
Exactly.
Then what exactly is an entity node if it doesn't contain the document's content?
An entity node is purely abstract structural metadata. It is generated by the LLM during that sequential extraction phase we discussed. It does not contain prose or markdown. It holds minute knowledge triples.
Triples?
Yeah, like subject, predicate, object. For instance, it is a Python object that maps entity, MariaDB to the type, system, and defines the relationship, Depantry and then to another entity.
Oh, I see. It's just a semantic signpost, the index at the back of the book telling you where to look, essentially.
Precisely. And because it only represents a conceptual relationship, the Python object physically does not have a .getContent function defined in its class structure. So when Vitali's terminal loop queried the graph for MariaDB, the engine grabbed all nodes associated with that keyword. It grabbed the chunk nodes and the entity nodes indiscriminately.
Ah, and the moment the loop iterated over an entity node and attempted to execute .getContent to print it to the screen, the Python interpreter threw an attribute mismatch error because you're asking a conceptual map for its paragraph text. But wait, if it threw an error, why did it print thousands of lines of log text to his screen instead of just halting the program and showing a standard Python traceback error?
Because Vitali had engineered a highly robust fail-safe mechanism into the terminal. His retrieval script was wrapped in a try-except-error handler. When the LlamaIndex graph engine encountered the attribute mismatch and threw the exception, the script didn't crash.
Oh, the except block caught it.
Right. The except block caught the error silently, flagged the graph search as a failure, and seamlessly handed the query over to his secondary standard ChromaDB vector search.
So the standard vector database caught the fallback.
Yes. And ChromaDB located the relevant file chunks. Since ChromaDB only stores raw text arrays, it successfully pulled the raw text and dumped it directly to the terminal's standard output.
And it just so happened that his specific note on MariaDB contained a massive multi-page list of Linux backup files.
Exactly. The terminal was simply streaming the exact, highly verbose text file he had saved. It wasn't an infinite loop. It was his failsafe executing flawlessly and returning exactly what it found via the fallback route.
That is incredible. The system was so resilient that a failure looked like a feature. But obviously, he doesn't want the graph engine to fail over to the vector database every time. He wants the graph to serve the unmodified file. So how does he patch that node traversal logic?
The patch is a single line of brilliant Python. He updates the memory traversal block in the script to explicitly inspect the class instantiation of the object before interacting with it. He adds an if statement. If no dot underscore underscore class underscore underscore dot underscore underscore name underscore underscore doesn't equal chunk node, continue.
So he intercepts the loop. The script looks at the metadata of the Python object itself, and if it identifies it as an entity node, it just skips to the next iteration.
Right, it completely bypasses the attribute mismatch because it only ever attempts to call .getContent on objects that is mathematically verified or chunk nodes. It perfectly illustrates why relying blindly on framework abstractions is dangerous. You can't just iterate over generic nodes in a complex library. You have to understand the specific object-oriented architecture underlying the data structure.
Right. So with the node traversal fixed, the graph system is stable. Vitally tests the runtime again. He asks the AI for a specific note, referencing it by its exact title. But the AI completely ignores the graph index. It bypasses the graph entirely and hallucinates a generic, resynthesized answer using the ChromaDB vector fallback.
Which is baffling at first glance.
Yeah, he fixed the crash, he fixed the node traversal. Why is the routing logic completely ignoring the precise graph index?
This failure highlights the fundamental limitation of processing raw, unformatted text through local LLMs for explicit data retrieval. Standard triplet extraction feeds the entire body of the note, thousands of words, into the LLM to search for entities and relationships.
It's just looking for nouns and verbs to connect.
Right. But this creates massive semantic noise. In Vitaly's Markdown vault, every single file begins with a standard YAML front matter block. He explicitly writes --title, quote, some title, quote, --, at the very top of the file.
Okay.
However, because LlamaIndex was feeding the entire file to the LLM as a single contiguous string of text, the LLM just treated the YAML header as standard body prose.
Oh, so the LLM didn't conceptually recognize that the string of text at the top was the definitive title of the document. It just saw it as more data to map.
Exactly. The system never explicitly isolated the YAML title into a searchable index key. So when he searched for the exact title, the strict string matching logic in the graph didn't trigger because the title was buried inside a massive chunk node of body text.
That makes so much sense.
Furthermore, passing thousands of full-length notes through an 8 billion parameter model to build these complex entity relationships incurs a devastating time penalty.
Yeah, let's quantify that time penalty for a second. His initial successful test on 20 files took several minutes. If he attempts to scale that heavy semantic extraction to his full vault of 3,000 files using a laptop GPU,
You are looking at uninterrupted hours, potentially days, of continuous GPU compute. The token generation speed and memory bandwidth constraints of the RTX 4060 mean that processing 3,000 files sequentially for complex triplets is practically unfeasible.
and a run of that duration risks hitting an unhandled formatting anomaly halfway through, crashing the script and forcing him to start over from scratch.
Which is an architectural dead end. So Vitaly makes a brilliant structural pivot here. He completely abandons the deep, full-body GraphRAG extraction framework. He writes an entirely new ingestion pipeline, which he names Graph Metadata Indexer .py.
Which is arguably the masterstroke of the entire build.
Well, without a doubt. He realizes that using a neural network to identify clearly formatted YAML header is a massive waste of compute. Instead of feeding the file to the LLM, he writes a pure Python regular expression script.
Good old Regex.
Exactly. This Regex script scans the raw text and instantly, deterministically extracts the YAML title and the tags from the top of the Markdown file.
So he bypasses the AI completely for the structured data. It's instantly fast, costs 0 VRAM, and is mathematically 100% accurate.
Right. And only after the strict metadata is secured does he invoke the LLM. He truncates the document, taking only the first 3,000 characters of the note, essentially just the introduction, and feeds it to Ollama.
Okay, and what does he ask it to do with that?
He uses a highly constrained, strict prompt. Give me a brief description of this content in exactly 1 to 2 sentences. Do not use filler or introductions.
So instead of asking the neural network to map every single conceptual relationship in a massive document, he just asks for a fast, cheap executive summary of the opening paragraphs.
The genius here is how he constructs the actual graph index. The nodes in his new NetworkX graph are not paragraphs of text or complex conceptual entities anymore.
What are they?
The nodes consist strictly of the Regex extracted document title, the Regex extracted tags, the 1 to 2 sentence LLM summary, and the absolute OS file path pointing to exactly where the Markdown file lives on his physical hard drive.
Wow, so it's no longer a deep semantic knowledge graph. It operates as an ultra-fast metadata interceptor.
Exactly. By bypassing the heavy triplet extraction engine for the body text, the indexing processing time plummets from minutes per batch down to just 2 to 4 seconds per file. He respects the physical limits of his silicon.
And this architecture completely redefines how the runtime retrieval operates. When the user queries the terminal for a note, the system scans the lightweight graph metadata, finds a matching title string, retrieves the absolute file path pointer, and then bypasses the AI completely to serve the data.
Yes, it uses native Python file operations to open the real, original Markdown file directly from the solid-state drive and prints it to the terminal screen.
It doesn't generate a summary. It doesn't use cosine similarity vector math to tape shredded chunks back together. It just hands you your exact note with 100% fidelity to the original markdown syntax.
This architectural choice completely eradicates LLM hallucinations for explicit file lookups. In standard RG systems, the AI will often drop critical punctuation in code blocks or hallucinate incorrect parameters because it is mathematically synthesizing an answer. Vitali's metadata interceptor guarantees you receive the raw data exactly as you wrote it.
Okay, so the metadata graph is lightning fast, the ingestion pipeline is finally optimized, but we are not quite at the happy ending yet.
No, we have one more hurdle.
Right. Vitali goes to test the terminal again. He types in an approximate search query looking for a note about SSH copying, and the terminal instantly crashes and throws a new exception. We've arrived at the final boss of framework engineering, routing and string collisions.
Yeah, framework abstractions are incredibly powerful until they break, at which point they become black boxes of obscure errors. When he searched for SSH copying, the Python interpreter threw the error. Stri object has no attribute retrieve.
It's always an attribute error. What exactly was shadowed in Python's namespace here to cause the code to think a string was a retrieval object?
So he ran into a classic framework abstraction trap. LlamaIndex utilizes a built-in method called asRetriever to handle query routing. In Vitali's custom query loop, he had assigned his search input, or the resulting node path, to a standard variable name.
Pretty standard practice.
Right. However, the LlamaIndex framework's internal state machine attempted to execute its asynchronous.retrieve method on that variable, assuming he was dealing with a complex instantiated retrieval class object.
Oh, no.
Yeah, because Vitali's custom code had overwritten that namespace with a primitive text string, the interpreter crashed. You cannot execute a complex retrieval function on a basic text string.
This is the inherent danger of relying on massive, opaque libraries. They do so much magic under the hood that if your custom code accidentally shadows one of their internal object states, the entire stack explodes.
Exactly.
And there was a secondary logical failure alongside a crash, right? The query for SSH copying failed because of a language mismatch.
Yes. Vitali's actual markdown file was titled in Russian 10 Primarov. Kopirovaný failov через SSH. Because the explicit English search string SSH copying was not a mathematical substring of the Cyrillic title, the strict title matching logic bypassed the file entirely.
So the framework crashed trying to execute a semantic search, and the strict string search failed because of cross-language rigidness. How does Vitali engineer his way out of this double bind?
He goes scorched earth on the framework abstractions.
I love that.
He completely deletes the LlamaIndex retrieval wrappers from the query loop. He stops using asRetriever entirely. Instead, he engineers a 100% pure, in-memory native Python dictionary scoring loop.
He replaces the AI framework's sophisticated search engine with a custom if-then Python script. Let's walk through the mechanics of that loop. How does he handle the cross-language matching?
The mechanics are beautifully straightforward and mathematically robust. First, the script dumps all the metadata nodes from the NetworkX graph directly into a standard Python dictionary in RAM. Then, it sanitizes the user's input, it converts the entire query to lowercase, and uses Regex to strip out all punctuation.
So it normalizes data.
Exactly. Then, it splits the user's sanitized query into an array of individual keywords. This is the crucial step for cross-language matching.
Yeah.
SSH copying is no longer a rigid phrase. It becomes two distinct, independent keyword strings, shush and copying.
So it doesn't matter if the surrounding words are in Russian as long as the acronym SSH is present.
Precisely. The script then iterates through every single node in the dictionary and calculates an integer match score based on a weighted matrix. If the explicit title of the file perfectly matches the input string, the file is awarded plus 10 points. If an individual keyword, like the English, matches a substring within the Cyrillic title, the file receives plus 5 points. If a keyword matches a word inside the 1 to 2 sentence LLM summary, it receives plus 2 points.
So it calculates the integers, sorts the dictionary by the highest score, and returns the top 2 file paths to the user.
It is entirely deterministic. There are no hidden object states to shadow. There are no asynchronous framework methods to collide with the namespace. It guarantees collision-free execution and allows for fuzzy, cross-language approximate matching without relying on expensive embedding vectors.
Which raises an incredibly important question for anyone listening who builds complex systems. Do we over-rely on black box frameworks like LangChain or LlamaIndex when a natively written 50-line Python if-then loop is actually significantly more robust?
I mean, framework wrappers are unparalleled for rapidly prototyping an application. But in highly custom, hardware-constrained environments, where you need absolute control over VRAM allocation and namespace routing, abstract libraries frequently become a liability. Falling back to native dictionary operations ensures ultimate stability.
It is bulletproof engineering. And with that namespace collision resolved, the architecture is finally stable, the CUDA crashes are mitigated, the node attribute errors are filtered, the framework routing collisions are bypassed.
We finally made it.
Yeah, let's zoom out and analyze the magnificent architectural beast that Vili has successfully deployed on his laptop. Let's break down the master architecture of the four-way router.
The final system operates as a completely private, offline knowledge base that effectively turns a consumer laptop into a deeply personalized agentic AI assistant. It relies on 4 independent but cooperating utility tools.
Let's spotlight each of these tools. Tool number 1 is vectorizer.py. This is his universal document ingestion pipeline. It handles the standard RAG vector ingestion into the ChromaDB database. But he didn't just plug in a standard recursive character chunker, did he? He wrote custom logic for different file types.
Right, because as we mentioned, standard text chunkers are notorious for destroying structured data, so Vili engineered custom layout parsers. He utilizes pipbf to extract clean text strings from PDF layers, bypassing optical character recognition errors. He uses Python docs to safely parse paragraph blocks from Word documents without losing the header hierarchy.
But the handling of Excel files is what really caught my eye. How does a standard RAG chunker ruin a spreadsheet, and how did he fix it?
Well, a standard text chunker reads a spreadsheet as a flat string of text. If you tell it to chunk every 500 characters, it will slice right down the middle of a row, completely separating a numeric value from its column header. The LLM loses the semantic meaning of the data because the 2D grid structure is destroyed. To solve this, vectorizer.py utilizes pandas and OpenPistol to intercept the file. It reads the entire Excel matrix, converts the data frame into a header-locked markdown table, and injects the entire worksheet into the database as a single, unbreakable vector chunk.
Oh, wow. It forces the database to ingest the table as one massive unit, eliminating token clipping errors.
Exactly. When the LLM retrieves it, it has the complete context of the headers and the rows, which prevents numeric reasoning fatigue and stops the model from hallucinating skipped data lines.
That is incredibly smart. And what about visual data? How is he handling complex text-based architecture charts like mermaid diagrams?
He integrated an automated LLM compiler into the ingestion script. When the script encounters raw mermaid diagram code, it doesn't just chunk the syntax, it passes the code block to Ollama during ingestion and prompts the LLM to translate the visual architecture into a highly descriptive plain text structural summary.
So you can search for the visual concept of the diagram, not just the code syntax.
Right. It stores that semantic summary alongside the raw code block in the vector database.
This vectorizer.py also features a Wikipedia API fetcher that pulls clean JSON summaries directly via REST, completely bypassing the heavy overhead of standard web scraping libraries. So that tool builds the dense semantic ChromaDB vector store.
Then we have the second tool in the architecture, GraphMetadataIndexer.py. This is the lightweight Regex pipeline we discussed extensively. It builds the low VRAM NetworkX metadata graph, mapping one ultralight node per markdown file containing just the title, tags, summary, and absolute OS file path.
This means he is running 2 entirely different databases side by side. The ChromaDB vector store is for complex semantic queries across a mixed corpus like asking, what did episode 3 say about RAG?
And the NetworkX graph database is exclusively dedicated to precision file lookups. Give me my exact unedited markdown note about MariaDB.
Which brings us to the core runtime application, tool number 3, vectorterminal.py. This is the interactive terminal interface where the user actually talks to the AI. It relies on a deterministic, intent-based 4-way router to decide how to answer a prompt.
Yeah, and this router is fascinating.
I picture this router as a highly caffeinated traffic cop standing inside Vitali's laptop memory. It looks at every single user prompt and instantly directs the query down one of 4 distinct highways based on the exact syntax of the request. Let's look at the precedence order of this routing logic, because explicit user intent always overrides semantic database searches. Highway number 1 is the recall route.
Right, the recall route is triggered by explicit ownership phrasing or conversational memory cues. If the user types phrases like, remind me, we discussed, you said earlier, or asks about my password, The traffic cop intercepts the query.
It completely bypasses both the ChromaDB vector documents and the NetworkX graph notes.
Instead, it accesses a local JSON file that contains the entire chat history of the session.
Highway number 2 is the note route.
This route activates if the pure Python scoring loop detects a strong graph match, specifically a score of 25 or higher, or if the user explicitly includes system keywords like volt or markdown. When triggered, the router uses the NetworkX graph to locate the absolute file path and loads the unmodified OS file directly from the solid-state drive.
And this route features 2 distinct execution submodes.
Correct. By default, it operates in strict retrieval mode, instantly dumping the raw text to the terminal screen. However, if the user's prompt includes analytical keywords such as explain, summarize, or translate, the router loads the raw file from the disk and then pipes the text through the LLM for active interpretation.
Highway number 3 is the docs route.
This is triggered by explicit corpus markers in the prompt, such as episode, transcript, spreadsheet, or diagram. This route executes a standard cosine similarity search against the ChromaDB vectorized documents to answer complex semantic questions.
And finally, highway number 4 is the zero route.
The zero route is the small talk short circuit. The script runs the user's prompt through a stop word removal function. If the remaining query contains fewer than one substantive keyword, for example, if the user simply types hello, thanks, or how are you, the router directs the traffic to zero.
It doesn't inject any database context at all.
Exactly. It prevents context pollution. Searching a database for the word hello is a massive waste of compute. The LLM simply answers the greeting natively, using its baseline weights, saving processing time and keeping the context window clean.
There is one more brilliant mechanical feature integrated into this runtime terminal: the Regex file system export interceptor. The LLM is capable of dropping physical files onto the user's hard drive on command.
This elevates the system from a search engine to a true agentic assistant, vitally programmed a Regex listener into the terminal's output stream. If the LLM generates the exact string token write file in brackets, followed immediately by a fenced code block, the terminal intercepts the output.
It automatically extracts the contents of the code block and writes it to a clean, formatted file within a dedicated exported files directory on the OS disk.
Right. You can literally prompt the terminal, pull my appmap pipeline diagram from the vault, and save it to my disk as appmap.mmd. And the AI will autonomously retrieve the data, generate the file format, and save it locally.
That is incredible functionality. And just to round out the architecture, the fourth tool in the suite is replacedata.py,
which is a precision purge utility. In standard RG systems, if you update a single document, you often have to re-index the entire database. This utility allows Vitally to surgically target and erase specific vector rows from ChromaDB, or wipe isolated metadata nodes from the NetworkX graph manifest, allowing for rapid data maintenance without the massive VRAM overhead of rebuilding the vault.
It is a breathtakingly complete, highly optimized system. But the most fascinating highway in that entire routing architecture is the first one we discussed, the recall route. Because the mechanics of how that conversational memory is handled brings us to the unexpected, emotional payoff of this entire deep dive. Let's talk about the ghost in the machine and the concept of the digital personality footprint.
This is where it gets really profound. Every interaction in the terminal, every single conversational turn Vitally has with his AI is serialized and saved to a local JSON chat history file named VitallyMainSession.json. But Vitally made a critical architectural decision regarding how that JSON file is queried by the recall route.
Right. The system is explicitly programmed to only mine the human's past dialogue turns as the conversational ground truth. Wait, why would he explicitly exclude the AI's past answers from the memory context block?
It is a safeguard against a phenomenon known as model collapse, or self-pollution. Human inputs are the absolute ground truth of the system. They contain teachings, formatting preferences, corrections, and explicit instructions. AI outputs, however, are past algorithmic attempts, some of which may contain subtle hallucinations, incorrect formatting, or flawed reasoning.
If you feed an AI its own past hallucinations as context for future answers, it will treat those errors as facts, creating a compounding feedback loop of degradation.
Exactly. To prevent this, Vitally engineered a prefix matching filter into the recall logic. The script scans the JSON history, filters out known AI refusal patterns and algorithmic outputs, and exclusively loads his own past human input into the LLM's context window. He labels this highly curated context block as personal knowledge from past dialogue.
The system prompt explicitly instructs the LLM to treat Vitaly's personal vocabulary extracted from this JSON block as the highest possible authority.
Yes, the human's local context overrides the model's baseline generic dictionary weights.
And because the architecture is explicitly designed to trust Vitaly's input over his own training data, a fascinating emergent behavior occurs. The model begins to adopt his specific linguistic footprint.
We see clear evidence of this shift from a rigid search engine to a personalized companion in the raw terminal logs. Vitaly actively teaches the AI Russian slang. In one session, he explains the nuance of the word poltrende, which translates to chatting casually, gossiping, or shooting the breeze.
And because of the recall root architecture, that definition becomes hard-coded into the personal knowledge context block. In a later session, when he asks the AI what the word means, it doesn't hallucinate a baseline dictionary definition. It perfectly recites the exact nuance back to him.
It learned it directly from him in session 1 and surfaced it flawlessly in session 2. He also instructs the model that the Russian word kruto translates exactly to the English expression cool. The AI seamlessly integrates this vocabulary into its own response generation.
It literally replies in the terminal. Now I can also use this word in our conversation, so let's chat casually and talk about something interesting.
This fundamentally reframes how we talk about humanizing AI. When massive tech corporations talk about humanizing a model, they mean applying RLHF reinforcement, learning from human feedback across millions of generic users to force a cloud model to act uniformly polite and safe. It's a sanitized corporate personality.
But by engineering an isolated offline language model that perfectly indexes your personal, uncorrupted markdown notes and learns its conversational tone exclusively from your filtered human input, you aren't just building a retrieval tool, you are meticulously constructing a localized digital footprint of your own personality.
The logs show the model mirroring his specific sense of humor and preferred vernacular. Vitaly types into the terminal, "We can switch to informal you, I won't be offended," and the AI adjusts its semantic output, responding, "You're right, we can use formality only when necessary. Now I will use you informally."
He even tests its contextual reasoning regarding text-based emotion. He asks if the AI understands his intent when he uses a trailing smiley face parenthesis, like a single close parenthesis character, which is a very specific informal typing quirk.
And the AI processes the context and says, "Yes, I understand. It means you want to add a little humor or playfulness to your message. I will take this into account when answering."
A genuine emergent rapport develops within the constraints of the terminal window. The literally types the phrase, "I'm just glad I have such a friend assistant in you. We are friends, right?"
And the model, leveraging the accumulated context of their slang and informal agreements, responds affectionately in Russian, "Yes, we are friends, and I'm glad you can feel comfortable with me. Now, if you are ready, let's talk about something specific. You asked for information about 4K video downloader. Do you want me to write you a detailed instruction?"
It seamlessly pivots from casual, personalized banter directly into executing a high-precision GraphRAG retrieval from his Markdown vault. It is not some monolithic server farm in California trying to guess what a million users want. It is an 8 GB VRAM laptop sitting on a desk, which has been mathematically forced through pure Python logic to become a perfectly tailored offline digital best friend.
This incredible synthesis of rigorous software engineering overcoming VRAM leakage, bypassing abstract framework collisions, writing pure Python extraction loops, and the emerging human connection that inevitably results from that level of personalization brings the story of Vitaly's GraphRAG journey to a beautifully poetic close.
It truly is a very long GraphRAG story with a very happy ending. To summarize the massive scope of this deep dive, Vitaly overcame suffocating hardware limitations. He neutralized geometric KV cache explosions by stripping out asynchronous framework requests and enforcing rigid, single-threaded sequential loops.
He avoided the memory bloat of JSON schemas by utilizing lightweight string extraction.
He survived the illusion of the infinite loop by deeply understanding the exact memory anatomy of LlamaIndex chunk nodes versus abstract entity nodes.
He bypassed disastrous framework string collisions by writing a 100% pure Python routing and scoring logic lib.
And ultimately, he deployed a flawless dual-engine architecture, a ChromaDB vector store, and a lightning-fast NetworkX metadata graph that functions as both a high-speed knowledge retriever and a personalized digital companion. He achieved what seemed physically impossible by intimately understanding the literal memory constraints of his hardware and writing bespoke code that strictly respected those boundaries.
Which leaves you, the listener, with a profound concept to mull over. As local quantized AI models become increasingly powerful and accessible, as they are engineered to fit into smaller and smaller hardware envelopes on our personal offline devices, are we moving toward a future where our most trusted confidants, researchers, and collaborators are bespoke, offline digital reflections of our own minds?
What would your digital personality footprint look like if a highly capable AI learned its entire worldview only from you?
It is a fascinating and entirely realistic frontier of personal computing to consider. We would be incredibly grateful if you subscribe to the RG to Riches AI channel on YouTube where this deep dive lives, and be sure to drop a like on this video and the other videos on the channel. It helps us continue to bring you these exhaustive explorations into the absolute bleeding edge of local AI development. Thank you so much for listening, and keep diving deep.